Here are the 200 most commonly used passwords worldwide released by NordPass, along with the time it takes to crack each one. For passwords like 123456 and password, hackers can crack them in less than a second. Is your password among them? How does it fare? Does it make you nervous enough to change it immediately? Don't rush just yet. Before you update your password, let's ponder a question together. How do hackers turn that jumbled string of characters into your plain text password? Are operating systems and websites really secure when it comes to storing passwords? In today's video, we'll thoroughly break down the entire process of password cracking and reveal how the first line of defense protecting your digital identity actually works. Are you ready? Let's get started. To understand why passwords get cracked, we need to explore two key dimensions: how passwords are stored in systems and the methods hackers use to attack them. In the early days of the internet, some websites stored user passwords directly in plain text in their databases. This practice is now considered a severe security vulnerability, but it existed in certain historical contexts due to a combination of factors, including technical limitations, lack of awareness, and cost considerations. It also led to many painful lessons. The core issue with plain text storage is that passwords lose any form of protection barrier. Once a database is compromised, all user passwords are directly exposed. For example, hackers can directly misuse accounts, whether through database theft, where hackers illegally download entire databases, SQL injection attacks, or server vulnerabilities. As long as hackers obtain the plaintext password database, they can directly use username plus plaintext password to log into user accounts. This allows them to steal private information, transfer assets, impersonate users to post unauthorized content, and more. As security vulnerabilities from early plaintext storage frequently emerged, the industry began adopting a smarter approach. Instead of storing passwords themselves, systems store the unique fingerprint generated by processing passwords through a hash function known as the hash value. The reason hash values can replace plaintext as the representative of a password lies in the three fingerprint-like properties granted by hash algorithms. Uniqueness, similar to one person, one fingerprint. The same plaintext password, when processed by the same hash algorithm, will always produce the exact same hash value. Conversely, different plaintext passwords, even with just one character difference, will produce completely different hash values. For example, these two passwords on the screen differ by only one character, but their generated hash values share no similarity. This ensures verification accuracy. When a user logs in, the system simply compares the hash value of the entered password with the stored hash value. If they match, the user's identity is confirmed. Irreversibility. A fingerprint is used for identification, not reconstruction. While a fingerprint can confirm a person's identity, it cannot reverse engineer their appearance or height. Similarly, a hash value is the result of a one-way calculation. It is impossible to reverse engineer the original plaintext password from the hash value. For example, even if hackers obtain stored hash values through database leaks, they cannot directly derive the original password like 123456. Instead, they only see a meaningless string of characters, for example, a 32-character hexadecimal string for MD5. This directly addresses the fatal flaw of plaintext storage. Even if data is leaked, hackers cannot directly obtain user passwords, fundamentally reducing the harm of such leaks. Fixed length. Regardless of whether the original plaintext password is 1 character long, for example, the letter A, or 100 characters long, for example, a complex string of random characters, the hash value generated by the same hash algorithm will always have a fixed length. For instance, the MD5 algorithm always produces a 32-character hexadecimal hash value, while the SHA-256 algorithm always produces 64-character hexadecimal hash value. This property makes storing and comparing hash values more efficient. Databases don't need to adjust fields based on password length, and systems only need to verify fixed-length strings during comparison, without incurring additional development or computational costs. However, even hashing is not foolproof. A hash function is a mathematical function that converts data of any length into a fixed-length, jumbled string. That sounds pretty secure, right? And since hash functions are one way, you can't directly reverse engineer the original password from the hash value. But here's the problem. If everyone uses weak passwords, hackers can pre-compute a dictionary containing common passwords and their corresponding hash values. This is known as a rainbow table attack. A rainbow table is essentially a lookup table of plaintext password and hash value pairs. Hackers use high-performance computers to pre-compute hash values for vast numbers of common passwords. For example, 123456, admin, birth dates, and dictionary words. They store these plaintext hash relationships in a database, creating a massive password dictionary library. When hackers obtain leaked hash values, they don't need to reverse engineer them. Instead, they simply look for matches in the rainbow table. If the table contains the hash value, they can instantly find the corresponding plaintext password. Additionally, if multiple users use the same simple password, their hash values will also be identical. Hackers only need to crack one of them to gain access to all accounts using that password, amplifying the risk. To To solve this problem, engineers invented salting technology. Salting doesn't replace the hash algorithm, but instead adds an extra ingredient to the password before hashing. This ensures that the same plaintext password generates completely different hash values, fundamentally neutralizing the threat of rainbow table attacks. Salting has become a core patch for modern password security storage. A salt is a randomly generated string unique to each user, typically 16 to 64 characters long. The longer, the more secure. It is generated by a cryptographically secure random number generator, ensuring unpredictability and uniqueness. Theoretically, the probability of two users having the same salt is close to 0. The salt doesn't need to be hidden. It is stored in the database alongside the user's hash value because its purpose is to participate in the hash calculation, not to remain secret. For example, if user A and user B both have the plaintext password 123456 but are assigned different salts, their generated hash values will be completely different. To crack a salted hash value, hackers would need to generate a rainbow table for every possible salt. However, the number of possible salt combinations is astronomical. For example, a 16-character random salt has about 16 to the 16th possible combinations. The storage and computational costs would be prohibitively high, making rainbow tables practically useless. However, the security of salting entirely depends on whether the salting method is implemented correctly. If all users share a global salt, for example, the system uses a fixed string as the salt, identical plaintext passwords will still generate identical salted hash values. Hackers only need to create a dedicated rainbow table for this global salt, rendering salting ineffective. Therefore, it's crucial to generate a unique salt for every new user. Even if two users have the same password, their salts will differ, resulting in different hash values. Moreover, if the salt is only 4 characters long, for example, ABCD, the number of combinations is only about 62 to the 4th. Hackers could still enumerate all possible salts and combine them with plaintext passwords for brute force attacks. Similarly, if the salt is generated using predictable information like user ID or registration time, hackers can guess the salt based on known information, significantly reducing the difficulty of cracking. The correct approach is to use a cryptographically secure random number generator to generate salts of 16 characters or more, ensuring the salt's unpredictability and uniqueness. Although salting neutralizes rainbow table attacks, it doesn't mean salted passwords are absolutely secure. First, it's important to understand that the core function of salting is to ensure that the same plaintext corresponds to different hash values. However, it cannot defend against targeted attacks on individual users. This is because each user's salt is stored in the database alongside their hash value. Once hackers obtain the salted hash value plus salt, they can directly launch targeted attacks against that specific salt. This is the foundation of cracking salted mechanisms. Hackers don't need to crack all users' salts, but can focus on a single target using their unique salt. Targeted brute force attacks, precise enumeration for a single salt. This is the most direct and commonly used method to crack salted passwords. The core idea is to use the target user's salt to enumerate all possible plaintext passwords, compute the hash value of plaintext plus salt, and compare. Hackers obtain the target user's salted hash value and salt through a data breach. They take a plaintext password from a password dictionary containing common passwords, dictionary words, birth dates, etc., or character combinations. They compute the hash value of plaintext password plus salt. They compare this hash value with the obtained hash value. If they match, the plaintext password is the target password. If not, they continue enumerating the next plaintext password. This method focuses computation solely on the target user's salt, without involving other user salts, making the computational effort concentrated. However, if the user's password is particularly complex, for example, a 12-character random combination of numbers, uppercase and lowercase letters, and symbols, the enumeration space would be about 95 to the 12th possibilities, which is currently impossible to crack with existing technology. Hardware acceleration, using powerful tools to break passwords. If salting is combined with slow hash algorithms, it can significantly reduce cracking speed. However, hackers can counteract this advantage through hardware upgrades, primarily by using high-performance hardware to parallelize computations of plaintext plus salt hash values. An ordinary CPU can only compute hundreds of bcrypt hash values per second, while a high-end GPU can compute tens of thousands per second. Hackers can build clusters with dozens of GPUs, increasing cracking speed by thousands of times. A task that would originally take a year could be shortened to a few days. Alternatively, they can use ASIC chips, similar to Bitcoin miners, customized for specific hash algorithms, for example, bcrypt. These chips far outperform GPUs in computational power. For example, a certain bcrypt ASIC chip can compute millions of hash values per second, specifically designed for cracking salted passwords. However, whether using GPU clusters or ASIC chips, the costs of hardware procurement and electricity consumption are extremely high. These methods are only used for cracking high-value targets. For example, enterprise administrator accounts, wealthy users' accounts, and not for ordinary users. Moreover, ASIC chips only support specific hash algorithms. If a system uses Argon 2, which dynamically adjusts computation logic, ASIC chips may not adapt, rendering their computational advantages ineffective. But there's no need to worry excessively. Despite the various methods hackers have, over 90% of salted passwords still cannot be cracked in real-world scenarios. The security essence of salting is increasing the cost of cracking to make attacks unprofitable. It cannot prevent hackers from launching attacks, but it can raise the cost of cracking to a level hackers cannot afford through the uniqueness of salts, the inefficiency of slow hashing, and the vast enumeration space of strong passwords. To fully defend against salted password cracking, efforts are needed from both developers and users. For developers must use password-specific slow hash algorithms plus unique long random salts for each user. Avoid using predictable salts, short salts, or shared salts. Use cryptographically secure random number generators to generate salts. Regularly upgrade hash algorithm parameters, for example, increase bcrypt's work factor as hardware computational power improves. And for users, always use strong passwords. Avoid common combinations like 1, 2, 3, 4, 5, 6. Avoid using birth dates, phone numbers, dictionary words, or other common terms. Use different passwords for different platforms to prevent one account leak compromising all accounts. Enable two-factor authentication. Even if a password is cracked, hackers cannot log into the account. That's all for today's video. If you enjoyed this easy-to-understand breakdown of computer knowledge, don't forget to give it a like and subscribe to the channel. See you in the next video.